Okay, so continuing example 4. So this is our transformed equation, right, in terms of v and x. And this equation is actually linear. It's a Bernoulli equation, but it's specifically linear because of our n. And so recall, well, okay, let me just write it out. So we have this guy is our p of x, and this guy is our q of x. And notice there is no y, so if you're looking at equation 9, right, it's usually q of x times y to the n. Well, I mean, this is really y to the 0, which is 1. So because I have this Bernoulli equation and my n is 0, because it could be n equals 0 or 1, then I know that this is linear. And this is great because now, since this is a linear first order differential equation, now we can use we can use section 1.5, which is using the integrating factor. And so that's what they did here. So again, if you want to look at, I'm referring a lot to equation 9 on page 63 of your book. Okay, so integrating factor. So we have rho, right, or rho of x. We have rho is equal to, remember, e, and we're integrating our p of x, and our p of x, of course, is this guy. Okay, so we have e, and we can take out our constant -3, so -3 integral of 1 over x dx. Well, this is nice because this is e to the -3, right? This guy is just the natural log of x. And let's see, I'll just continue over here. And we're working with a logarithm, right, our natural logarithm, so I can use properties of logarithms and rewrite this as e to the ln of x to the -3, right? This guy is really a power. And then this is really 1, so we're just left with x to the -3. So that's what my rho of x is. Okay, so let's multiply our rho of x to both sides of our differential equation. So we're left with, okay, so we have, this is our rho of x, so I'm really going to multiply x to the -3, right, times all of this, and of course times the right-hand side. And after distributing our integrating factor, right, to each term, and using some algebra, right, just some law of exponent rules, we obtain x to the -3 dv dx minus 3x to the -2 v equals 4x to the -2. Again, I'm just using some law of exponent rules. And then this is very nice because then we notice this guy is the derivative, right, our dx with respect to x of this guy, which is what we have been doing when we when our differential equation is linear. And we are, well, we can maybe we can rewrite this as, that's not a 3, that's a 2. And we're almost done here because we can definitely integrate with, both sides, right, with respect to dx. And move this up a little, and we love integration and differentiation because they're inverse properties, and so that's gone. So we have x to the -3v is equal to, and then if we integrate this guy, okay, so if we show the work, this is really 4x to the -2 dx, and again, and I strongly encourage that you show your work when you're integrating, even if it's an easy polynomial function that you're integrating, or a square root function or a cube root function. Again, because I mean, you can technically input this in your in a computer program. You can use your graphing calculator. But if you want partial credit on your test or on your homework, I need to know that you know how to integrate this function. Otherwise, if I just see an answer and you get it wrong, well, I mean, I can't really follow your thought process. So again, I encourage you to write every step, even if you already know how to do it, in your head, because I can't read your mind. I don't know what you're doing in your head if you're doing it in your head. Okay, so continuing the integration process. So we have 4 times, let's see, x2, we're adding 1, right? And that's going to be negative, plus our constant of integration. Whoops. And let's move this up. And we can write this as the following, right? And again, this is just some constant. If you want to call it kc, we can just leave it as c. It's still an arbitrary constant. And recall that our goal, right, well, we had a function of x and y, and we wanted to transform it to a function of x and v, right, to help us determine that this was, in fact, linear. So we have our x and v, right, but we have to go back. What was our v? And our v, if you go back to the top of the problem, v was y squared. So we can rewrite this, and then we can just call this c. And remember, we're looking for our solution to a differential equation, right? Some function of x. And in this case, right, if we solve for y squared, right, I can divide both sides by x to the negative 3, and then use, of course, with algebra, we simply get this guy. And this solution, right, is, we cannot write this explicitly because, I mean, if we solve for y, we actually get, we would multiply both sides by 1/2, right, or you're really taking the square root. So we're going to have 2 solutions. So you can write it like this. I believe your homework assignments usually leave it like this. I mean, because we know that this really means this. You have a positive and a negative solution. Okay, so I'm going to do 2 more videos, which are the examples in the book, examples 5 and 6. Again, they just have some really good cases, and I really want to work those out. Again, you're more than welcome to read the book if you'd like. Although I do just add some intermediate steps and, you know, some hints every here and there for your exam. One more thing I wanted to say. Okay, so I received, let's see, no, actually, I didn't receive any specific homework problems on 1.1 and 1.2, but I noticed on some of your homework assignments that your solutions were incorrect, or you weren't sure how to attack the problem. I encourage you to ask me questions, or if you don't want to ask me questions, ask your classmates on the discussion board. I mean, I'm here to help. I will give you hints on the homework. I mean, I want you guys to get a, 60 out of 60 on your homework. So for this section, for example, in 1.6, when I assign specific problems, right, if you're not sure, is this a Bernoulli equation and you want to ask me, or you're not sure about your substitution method, again, I can guide you to it. Again, I'm here to help. If, I don't know, maybe this class will get 100 out of 100 on the first exam, and that's great too. But again, I'm here if you need me. I'm more than happy to do some fun differential equations in my spare time. Okay, I will see you guys in the next video.